Hi, I'm Hemang Chawla. I am pleased to present our work, Continual Learning of Unsupervised Monocular Depth from Videos, done along with my colleagues Arna Verma, Ilahayarani, and Behram Zonos. The capability to estimate scene depth has found applications in augmented reality, autonomous navigation, and more. With the increasing demand for cost-effective, lightweight, and flexible depth estimation solutions, camera-based methods have emerged as a promising alternative to the use of LiDARs, especially unsupervised depth estimation methods from single images that do not require ground truth labels. These unsupervised methods potentially allow the training of depth estimation models on crowdsourced videos with unknown camera intrinsics. Nevertheless, it remains an underexplored problem due to the challenges associated with the standard training protocol. Within the standard training protocol, the models are retrained from scratch on all the available data after new data is collected, thus incurring high computational time and energy costs. Furthermore, to ensure that the models can be updated in the future, it is necessary to continue storing all the collected data post-training. Instead, the continual training protocol involves incremental training of the model on sequential data from different domains. Continual learning is also necessitated for practical deployments, such as in the case of a self-driving car or robot navigating through various locations, or when adapting models pre-trained on simulated data to real environments. Additionally, privacy considerations may be necessary in scenarios where the robot does not have permission to store all data on the server and has limited onboard memory. However, adapting the model for the new domain is not sufficient, as it must maintain its depth estimation capability on earlier domains as well. Therefore, there is a fundamental dilemma between maintaining the stability of the old information and the plasticity to adapt to the new information for continual learning. Naive continual learning without a strategy to handle this dilemma will result in catastrophic forgetting, as can be seen in the figure. While several continual learning methods have been utilized to address the stability-plasticity dilemma for image classification, such methods for depth estimation are lacking. Additionally, depth estimation poses a distinct challenge because of its high-dimensional output space and the requirement to make highly correlated predictions through the use of local spatial relations within images and temporal relations within videos, where the depth at one pixel may depend on the depth at other pixels. Thus, there is a need for a framework that includes a set of sequential tasks that represent these challenges, as well as suitable metrics for evaluating the performance of the models. Hence, we introduce a framework for continual unsupervised depth estimation, CUDE, to overcome this gap. CUDE consists of 4 tasks, each on a different dataset with unique characteristics representative of the challenges of domain and depth range shifts across simulated or real and indoor or outdoor scenes. CUDE includes performance measurements for continual learning using 3 metrics. We compute the error and accuracy of depth estimation on each task after training a specific task to generate a task-wise performance matrix, A. Then, the first metric, final average, measures the mean performance on all tasks after training the model on the final task. The second metric, overall average, measures the performance over all the scene tasks after training the model on each task. It indicates the improvements and degradations of model performance as the model is trained on different tasks. The third metric, stability-plasticity trade-off, SPTO, measures how well the model tackles the dilemma between retaining performance on the previously seen tasks and the capability to learn new tasks. With the CUDE framework, different methods can be devised for continual learning of unsupervised monocular depth estimation. Many state-of-the-art monocular depth estimation methods simultaneously train monocular depth and ego motion networks on consecutive images from videos. The estimated depth and ego motion is used to reconstruct the target image from neighboring source image using perspective projection transform. This requires knowledge of camera intrinsics, but can also be learned along with the depth and ego motion if unknown. Photometric and smoothness losses are applied between the synthesized and original target images, usually while masking some pixels that violate camera motion assumptions. Here, we introduced MonoDepthCL, a continual learning approach that is inspired by the complementary learning systems in humans. It postulates that humans learn continually through interactions between complementary systems that are learning at different rates. This includes a fast-working system adapting quickly to new experiences and a slow context system consolidating knowledge from the fast systems. The fast and slow systems help model plasticity and stability in learning, respectively. Thus, we formulate MonoDepthCL as a method with dual memories and replay. Specifically, there are two models: working model, which is learnable, and the context model, which is maintained as an exponential moving average of the working model. For replay, we employ a bounded memory buffer updated by reservoir sampling, which allows the buffer to approximate the distribution of samples seen by the models. By updating the context model with a small frequency, it helps to address forgetting in the context model. Furthermore, we distill the knowledge of the consolidated representations of memory samples from the context model back to the working model to align its learned representations on new tasks with previous tasks. Since depth estimation involves training via view synthesis, we ensure consistency in the synthesized targets between the context and working models. This guarantees spatial consistency in the consolidated depth maps of the target images and temporal consistency in the poses between the target and nearby source images. We refer to this as spatiotemporal consistency. The models are trained on a combination of spatiotemporal consistency loss and depth estimation loss. To reduce the overfitting to buffer samples, improve invariance through augmentation, and improve efficiency, we randomly crop these per pixel consistencies before evaluating the final spatiotemporal consistency loss. We sample the ratios to be cropped for each consistency for a Gaussian distribution. These cropped losses are then averaged across all predictions, source images, and crop pixels to get the final consistency loss. We also use a warm-up for the spatiotemporal consistency loss, such that it is only applied after the first task is learned. This allows the view synthesis to be learned well before it is used as a constraint between the context and working models. We compare proposed MonoDepthCL against naive continual training and training on the whole dataset, that is, the joint distribution after collecting data from all tasks. These form the lower and upper bounds for continual learning, respectively. As shown, there is a significant drop in performance of naive continual training on each task as newer tasks are encountered, in contrast to MonoDepthCL, which undergoes far less forgetting across tasks. We further compare against generic experience replay approach to continual learning without a stable context, and also context depth itself that maintains an exponential moving average of the working model. We show that MonoDepthCL outperforms other continual learning methods for different buffer sizes across all methods. Particularly note how MonoDepthCL is equipped to handle the stability-plasticity trade-off compared to rehearsal-based experience replay. The stronger SPTO performance of MonoDepthCL also translates to lower task recency bias. The distribution of performance across previous tasks after learning each task is more uniform for our method than for experience replay. Next, through an ablation study, we examined the two major design components, warm-up and random cropping. Warm-up is applied during the first task to allow the view synthesis to be learned properly before it is applied as a constraint between the working and context models, and random cropping of the spatiotemporal consistency map introduces invariance through augmentations and improved efficiency. Both of these contribute to the continual learning performance for our method as shown. Next, to examine the extensibility of MonoDepthCL to longer task sequence, we also present CUDE 5, consisting of an additional fifth task with domain shifts and double the depth range than task 4. We observe that MonoDepthCL continues to mitigate forgetting and improve performance through spatiotemporal consistency. Finally, we examine the ability of MonoDepthCL to continually train on crowdsourced video sequences where the camera intrinsics are not available and must be learned in parallel. We show that MonoDepthCL outperforms naive continual training across all final average metrics. Although a considerable gap still exists between joint training and MonoDepthCL, our study represents the pioneering effort towards crowdsourced continual learning for unsupervised monocular depth estimation. In conclusion, our work showed the importance of continual learning in unsupervised monocular depth estimation. We introduced CUDE, a framework for benchmarking continual learning methods for unsupervised monocular depth estimation in real-world challenging scenarios across domain shifts, along with metrics to compare how different methods handle the stability-plasticity dilemma. Finally, we proposed MonoDepthCL, a dual memory replay-based method with new spatiotemporal consistency loss, and show that it reduces catastrophic forgetting even when the camera intrinsics may be unknown. We hope that this work will serve as a foundation for future research endeavors in continual unsupervised depth estimation. Thank you.